That you're recording, and I do have audio. When last we met, we talked about Gauss's law, and because I was in a big fat hurry to try and, well, I bet that went over great in the recording. I was in a big fat hurry trying to get cover the material so we could be caught up, and I gave y'all some bad information on that Gauss, working that Gauss problem, that Gauss's law problem. Now, that said, I want to say I was duly impressed by a couple of you who, despite my misinformation that I gave you being in the big old fat hurry, a couple of you still managed to, apparently by reading the chapter, figured out the right way to do it and got the homework problem right, despite my giving it to you wrong. Now, for those of you who just were stupid enough to just trust me and write down what I said, that I did not hold that against you. So I didn't dock you for that problem when I was grading the homework. Here we go, Cyrus. Got you a lab and a couple of homeworks. Get back to you. 1 and 2. So, who here picked up on the error? When we were talking about using Gauss's law for that homework problem, had you calculate the area, the surface area of that cube of however many centimeters on its side. When they gave you the flux, the total flux coming out of that cube, they had already done that summation. Okay? Well, this one's going in the trash now before it. The sum of the E field perpendicular to each little unit of area added up over the total closed surface of the Gaussian surface, in this case that cube, equals the total flux. This is the value they gave you in the homework problem. There was no need to go in and calculate the surface area. That had already been done. That was equal to the enclosed charge divided by epsilon sub naught, which we related to K as K equals 1 over 4 pi epsilon sub naught. So, like I said, 2 or 3 of you got this right on the homework anyway. So, to those of you who did, kudos, good job. I'm impressed. To those of you who did not, I'm sorry, I gave you bad information because I got in a big hurry and I shouldn't have. Now, we are going to use Gauss's law some more as we pass through this next section on the electricity, electric potentials. But today, being caught back up, we're going to start with chapter 17. And we're going to talk about electric potentials. This is why I've had you working on that lab, calculating that vector field of an E field. tomorrow, you're going to actually measure some potential equipotentials, and you're going to plot them out on that same piece of paper. And in that way, hopefully, this is going to make real for you the relationship between electric potential and the electric field. Okay, and that's the whole point of this. The E field is what is actually exerting the force. But that force is generally measured in terms of, we don't have meters that can measure the E field. We actually have little meters called Gauss meters that can directly measure a magnetic field, the B field. And it'll give you the vectors because it measures it perpendicularly to the to the probe. So you put the probe in a field and you hold it vertically and you get a direct measurement of the horizontal component of the magnetic field at that point. Rotate it 90 degrees, you measure the vertical component. Spin it around and point it that way and you get the third axis. You can literally, I've done it, you can physically directly measure a magnetic field in 3 dimensions. It's tedious as a bugger, but you can do it. We don't really have anything to do that for an E field. What do we have? What do you use when you measure electric force? You're all in some form of the electrical program, right? A what? A multimeter. What do you measure when you're measuring electric force? No, that's current. Have you heard the word electromotive force? EMF? What is that when you're measuring EMF? You're measuring voltage. And that's what we measure. That's what potential. The quantity is the potential. It's, mathematically speaking, it's the gradient of the electric field. We're not doing this on, we're not doing the calculus-based version of physics, so we're not going to deal with the gradient of the electric field, but that is what is the potential, is the gradient of the electric field, and hopefully that's what I'm going to show you today. And more importantly, that you're going to measure it for yourself tomorrow whenever you come back for lab. Now, how many of you remember from Physics 1 the last time you worked with a field force that had gradients associated with it? What was it? What's the only other field force you've worked with? Non-contact force. Gravity. You plotted the gradient of the gravity field. Maybe you didn't. But the one thing you did notice was that it was a conservative force. Right? There was a certain potential energy associated with an object that had nothing to do with anything except where it was physically inside that gravity field. The higher up it went, the more potential energy it had. The closer it got to ground, the less potential energy it had, the more kinetic energy it had. Remember conservation of energy? Total potential energy plus total kinetic energy minus work done by non-conservative forces was always equal to 0. The change in the energy, potential and kinetic, was equal to what? The change in the potential energy was equal to the negative of the work done by the force, by the field. Okay? That's where we're going to start today. The work done on an electric charge is equal to The force exerted on it times the distance that it's exerted, that it travels. Does everybody remember that from Physics 1? Work equals force times distance. But in this case, we know we have an expression for that force. The electric force, the force exerted on a charged particle by an electric field, is Q times E. The charge of the charged particle times the electric field is equal to the force exerted on that charged particle by the electric field. So we can then say the work done by the electric field is equal to the charge times the electric field times the distance the particle is moved. We also, obviously we know that we're dealing with potentials here, the gradient of that electric field. We're not there yet. Whatever potential is, we've got some electrical potential energy at a point A. Which way did they do the subscripts? Yeah, of course. They did them backwards. Point B minus the potential energy electrical at point A. What we're saying is we have a charged particle in some uniform electric field. And we move it from point A through some circuitous path. It doesn't matter what path we choose, but we move it to point B. Okay? It is at some potential energy here at point A, and it is also at some other potential energy here at point B. If we take the difference in that potential energy, the change in potential energy from the final potential minus the initial potential, that will be equal to the negative of the work done moving it from point A to point B. But the work is simply Q times the electric field times the distance. So it's going to be equal to minus the charge of the particle times the electric field times the distance it moves from B to A. More specifically, the displacement. Because this is a conservative force, so it doesn't matter what path you follow. Do y'all all remember that distinction? If you took Physics 1 from me, you should, because I reminded you, I pointed out to you then, when we first started talking about this, that there's a difference between distance and displacement. That's why there's a difference between speed and velocity. The average speed of a car in the India 500 is a couple hundred miles per hour. The average velocity of the winner of the Indianapolis 500 over the course of the entire race is 0, because they end up at exactly the same place they started. No displacement, no velocity. I told you back then that this had to do with conservative forces, and we did use that fact to develop our understanding of the conservation of energy and potential energy and kinetic energy and all the rest of it. Well, now the same principles apply in this electric field because this is a conservative force. The change in potential energy is equal to the negative of the work done on the charge. Now, you recall last chapter, we were talking about we first introduced Coulomb's law, and we found that it was convenient to define the electric field, this vector field, as force per unit charge, right? Remember that? Coulomb's law? And then we said, well, if we define an electric field, E, as the force per unit charge, or here, let me keep the numbers the same, force per Q, per unit charge, then that would give us K Q1 Q2 over R squared divided by that charge, that unit charge, which left us with E as K Q1 over R squared. And that's how we came up with our E field. Any of you who have taken calculus may be able to look at this and realize that all I did was I took a derivative. Okay? If not, don't worry about it. Similarly, we're going to define potential energy and we're just going to call it potential because we're going to assume, at this point in class, it's too tedious to try and continue to remember to say electrical potential energy, but we're talking about electric fields, so everybody just pretend like it's understood that in the context of this class, we're talking about electrical potential energy. We're going to call it the potential per unit charge. So if we take potential energy and divide it by Q, that becomes our potential energy, what we will call volts. Or, in particular, in relation to the drawing over there, this would be PEA, would be the voltage at A. So the potential energy at A divided per unit charge is the voltage at A. How many of you remember seeing Ohm's law written? I'm sure you've all seen it as voltage equals current divided by resistance, right? Or R equals I times V, or I over V. Aside, never mind how you can rearrange it. How many of you remember ever seeing it as E equals I over R? You did. You don't see it that way anymore for a reason. Too many people were seeing E and calling it, well, doesn't matter. The point is it was called E instead of V because they were talking about electromotive force. When we measure electromotive force, we measure it in terms of voltage. Okay? That's this potential per unit charge that we are talking about here. Now, If we talk about the change in potential energy, because every time you measure voltage, you always measure it relative to some other point, correct? Usually ground. So it's kind of difficult to, have you ever used a voltmeter with just one probe? No, you can't. You can't just stick it in here and say, okay, look, this table is at electric potential or voltage of V. You have to have a reference to measure V relative to. In this case, ground. In most cases, ground. So, for that reason, that's kind of meaningless, or it's certainly not practical. But we can talk about the change in potential. As the change in voltage. And we can solve this as the change in potential energy as the unit charge times the change in voltage. Which this you will find written as V sub BA, meaning the potential, the voltage from B to A, or the potential difference. Before I get too far ahead of myself, what else do we know about this right here? PE over Q. The change in potential divided by Q is equal to the negative work done by the charge. If we divide that by Q, we're left with voltage from B to A is equal to the negative of the electric field times the distance. And that's the distance from B to A. How many, while I'm talking about this, I want to point out that the volt, it itself is a unit. But what is it in what is it in terms of other more fundamental units? The volt, by definition, is equal to 1 joule per coulomb. Okay, and you do want to remember that because we're gonna come to some units of energy here pretty quick called electron volts that are going to make a lot of your homework problems a whole lot easier to do. But they can be confusing. So we've got the change in potential is equal to electric field times distance. Well, I wish this was... Okay, well, at any rate, what we've got here is this change in potential is simply equal to the charge, the unit charge, well, see, this is why it can get confusing. We talk about the unit charge like we normally think of it as an electron is a unit charge, or a proton is a unit charge, which is a certain number of coulomb, 1.6022 times 10 to the minus 19 coulombs. So it's, in that case, we think of it as a physical property as well, or physical entity, as well as, but then it starts getting treated like it's just a unit. And it can get confusing. It's like when we talk about position is simply location. It's a distance in meters. Okay? But then we talk about how fast a position changes per unit time. Okay, well, what is that unit of time? 1 second. That's the fundamental unit of time. So when we talk about speed, we're talking about change in position per unit time, or meters per second. Here we talk about a volt as joules per coulomb, or as energy per unit charge. What's the unit of charge? It's a coulomb. Okay, so of course the unit charge is also quantified in that an electron is the smallest fundamental unit of electrical charge you can have. Is 1 electron's worth 1.6022. It doesn't get defined in a nice convenient way where there's 1 unit of electric charge that's the fundamental unit. 1 second is 1 second, and it works out nicely that way. In this case, we have to keep this straight. We're not talking about an electron, we're talking about a unit of charge, coulomb. An electron is a physical entity that has a certain amount of a certain number of coulombs. Here we're talking about a number of joules for every coulomb of charge. Okay, so then I set up this and I talk about an electron or some little unit of unit charge being moved across this potential. And I tend to think of that as, well, think of an electron being moved from point A to point B in a field. But what I'm telling you is don't try to think of it as an electron. Think of it as a unit of charge. Think of it as a single coulomb if you want to. I know that makes it a very big charge. A coulomb is, well, 1 coulomb per second is 1 amp of current. But anyway, when you move a fundamental unit of charge across 1 volt of potential difference, how much energy have you used? One joule. 1 volt of potential difference is 1 joule of energy for every coulomb you move across that potential difference. Okay, is this starting to make sense now? Let's do this example here, the conceptual example 17.1. It's on page 475. Let's work through this. I think this might help sort all of this out for you. I'm going to not erase that yet. Make some room over here. Okay, we start with 2 parallel plates. And we're going to ignore the fringing effects at the edges and look at the uniform E field in the middle of the plate. Now we take an electron, a negative charge, and we put it over near the negative plate. Right here. That's an electron. If the electron is free to move, will its electric potential energy increase or decrease, and how will the electric potential change? So let's take this one step at a time. First of all, we know if this is an electron and we release it over here at the negative plate, it's going to move to the left. It's going to move over to the positive plate. It's attracted to the positive. It's repelled by the negative. So it's going to move from here over to here. And it will come to rest on the surface of that positive plate. What happens to its velocity?
Goes up.
Over here, we release it initially from rest. We let go of it, and it is moved here, where just before it hits that plate, it is now traveling with some significant velocity. Everybody see that? We let it go here, and it accelerated until it was traveling at some finite velocity just at the instant before it hits that positive plate. That means the potential energy it had when we released it at rest was converted into kinetic energy. Conservation of energy is still true. So, whatever its total energy here, whatever its total energy was there, well, we know its kinetic energy was 0 because it was at rest. It wasn't moving. We let it go, and it accelerated to here. So, its total energy here must still be equal to that same amount of energy total. But since kinetic energy is increased, its potential energy had to decrease. Its potential energy became whatever its total energy was to begin with, minus all of that new kinetic energy it acquired. So, in order for an electron to go from this negative plate to this positive plate, its potential energy had to decrease. Okay? As the kinetic energy increases, potential energy has to decrease. That's always true.
Vice versa.
As if, yeah, well, yeah.
Potential energy increases, kinetic energy decreases.
Unless there's some outside force acting on it, yeah. Well, and in this case, the kinetic energy would decrease to zero when it hits the plate, but at that point, it's being acted on by an outside force, the plate. That's like you drop the marker from here, it's going to accelerate till it hits the floor. Once it hits the floor, it comes to a screeching halt. But the floor is not the gravity field. The gravity field is this invisible force, this between it, this non-contact force. The floor is a separate entity. Same thing here. The plate, the field, the plate may be instrumental in producing the electric field in that it's charged positively in producing the electric field out, causing it to emanate outward from there. But the plate is not part of the electric field. Just like the floor is not part of the gravity field. So, what work was done on this charged particle, on this electron? Work was done. It went from here to here. A force was exerted because it accelerated, and it was exerted over a distance from here to here, so that work was done. And that work, was it positive or negative? Nope.
Positive.
Positive work was done. What does that mean? Yeah, I'm going to stop you right there. It has nothing to do with direction. This is strictly about the relative potential in the field. The work is equal to the negative change in potential energy. No, this is the change in the potential energy we just saw was a negative change. It went from a
So therefore that cancels out that negative right there.
the potential energy went down, so it was a negative change in potential energy. And the work was then positive. These signs for work, change in potential. They're going to confuse you because the charge can be positive or negative. How would this have been different if we had been working with a proton instead of an electron? And let's suppose that we put a proton right there. It's already it's already at its lowest potential point. No work because there's no change in potential. There's no force times distance. I mean, there's some force pushing it up against that little plate, but it's not moving. It's like there. There is a force acting on that marker. It's a gravitational force pulling it down. There's also a normal force pushing it up from the table. Same thing here. There's an electric force pushing it into that plate. There's a normal force of the plate pushing it back that way, stopping it from going anywhere. They cancel out. No network. No work is done. No change in potential. If it was a positive, now in this case it kind of makes sense that the potential energy went up because you went from a negative potential here to a positive potential there. But it didn't go up. The potential went down. Even though you went from a negative to a positive potential, the potential energy went down because the kinetic energy went up. If this were a proton and we put it over here, then it would be accelerated this way and the kinetic energy would increase, which would mean a decrease in potential energy. But in this case, you would be tempted to see the going from a higher potential to a lower potential as being a decrease in the potential. That is only true if it's acting on a positive particle. As soon as the sign of that charge changes, that all changes. So, make mental note of this. Change in potential of the particle, of the charge, do not rely on the sign of the potential going from positive to negative, meaning a decrease in potential. Positive to negative potential is a decrease in potential for a positively charged particle. Positive potential to negative potential is a decrease in potential, is an increase in potential for a negative charge. If we put an electron over here, how would its energy change?
That would be decreased, right?
It wouldn't. It would just be stuck there.
It would be the same thing as the proton.
Same thing as putting a proton over here. Yeah. If we then go in and push this electron from here to here, now what is its change in potential? No. This would be an increase in potential for a negative charge. Remember, the change in potential is times, think of it as multiplying it by the sign of the charge. So if the potential goes from positive to negative, but it's times a negative charge, that's a net. It's like multiplying a negative by a negative, you get a positive.
So that's an increase if it went from positive to negative with the negative charge.
Exactly. That's an increase in potential.
Okay, so positive, if it went from positive to negative, it would be a decrease.
If an electron goes from negative potential to positive potential, that's a decrease in potential for a negative electron.
So it has to start from the same charge, I guess, plate in electron, proton, and if it moves to the other side,
exactly.
That's an increase.
All you have to think about, if to really keep this straight, you're exactly right, but I'm telling you the simplest way to keep it straight in your head is just think about like charges repel and opposite charges attract. When you release the particle from rest, When the particle is free to move, which way is it going to go? Is it going to be pulled that direction? If it is its kinetic, that means its kinetic energy is going to increase. And if the kinetic energy increases, the potential energy decreased. Okay? We also have to talk about who or what did the work. Work was done, moving it from here to here. It was equal to the negative of the change in potential. The potential went down, the negative, the work was positive. What if we went from here to here?
How is that possible? How can an electron start from a positive and go to the negative?
If we push it.
Oh, okay.
So what if we push it? What if we push the electron over here and then pin it and we hold it there? What happened to its potential? Its potential energy went up. No, not in this case. Why did it go? Because I pushed it. Okay? That means, remember, the whole principle of conservation of energy is about conservative forces. In other words, if something happens without the influence of an outside or external force, okay? Once the electron gets to that positive plate, the positive plate becomes an outside force and stops it and exerts a normal force in the other direction. Right.
But it's effortless if you put an electron on the negative side because it's attracted to it. So the potential energy goes down.
The potential energy goes down because the work was done by the force, by the field. When we did the work, the potential energy went up. So what work was done? What was the work? The work is equal to the negative of the change in potential. So if we did the work, it would be negative work. And that means, that's what the negative sign would imply on the work. If the work is negative, that means it was done by an outside force, by an external force, not by the conservative force. Okay? Now, or it was negative. Negative work is work done by a non-conservative force or by an outside force. Just think about it this way. You put the electron up here and then you let it go. It moves because of the field doing the work. That's going to be an increase in kinetic energy and therefore a decrease in potential energy. It's going to make the work positive. What if it's a proton?
Start from the negative side?
Right?
Then it would stay there.
No, proton's starting on the positive side, going to the negative side.
You would have negative work at that point.
Why?
Because you're having to push on it to make it move.
No, if it's a proton, it's moving itself.
Yeah, it would be the same thing as whenever you had an electron on
going the other way.
Yeah.
Your potential still goes down. The potential energy goes down because the kinetic energy goes up. Now, in this case, it's convenient to go, oh, well, I went from a positive to a more negative potential, so the potential went down. That's a bad way to think about it. It's not incorrect, but it's confusing because that's only true as long as it's a positive charge. As soon as you throw in a negative charge, everything gets reversed. If you think of it as the potential went down because the kinetic energy went up, strictly under the influence of the field, then you still have the work as the negative of the change in potential, which is a negative change in potential, which is a positive work, which means it was done by the field.
The only reason kinetic energy isn't going up when potential energy is going down, whenever you have, you're having to push it, is because you're having to push it.
because it's a non-conservative or an external force
So if the force is
that's at work.
if the force is pulling the charge, then that would be true because the kinetic energy is going up while the PE is going down.
Right.
Okay.
It's a conservative force. This is a conservative force, this electrical field. Okay, and so just by changing in your change of your potential energy is what causes the kinetic energy to increase. Think of it as a hill. Think of a hill, and you set a ball or a skateboard or something at the top of the hill. It starts rolling down, it gets faster and faster because gravity is pulling it down. And its potential energy is decreasing as its kinetic energy increases. Same thing here. Remember that we talked about potential as force, the change in potential as force times as the negative of the work, negative of the force times the distance. What you're going to find is, where's it in the book here? Yeah, right here in, it's actually the same example we've been talking about. The magnitude of the electric field. Wait, is this the same problem we were working on? No, it's not. This is another, yeah, I turned a page and didn't notice. Let's look at this. Work is negative Q all right? But that same work is also equal to force times distance, which is equal to, what was it? What's force? Q times E times distance. So we have Q we have work, which is Q Q times E times D, which is equal to minus Q times V sub B minus V sub A, change in potential energy, or change in potential, change in voltage. Well, if we divide both sides by Q, we end up with the E field times the distance is equal to the change in potential, or the change in voltage. It is. But the point that the point I'm looking to make here is that the electric field is actually voltage per unit distance, or volts per meter. Do you see that? You ever seen, we use the analogy of gravity versus as gravity compared to electric field. Have you ever seen, what do they call it? Not isobars, but isotropics. Isotropical, not isotopes, isotropic. Isotropic lines on a map. We want to plot a two-dimensional map. So you start off with these uniform elevations. Okay? And now to plot this map out in 2 dimensions, you have the lines of this elevation that are this far apart. Well, this one is going to be a little bit closer to that one. And this one's going to be even closer than that. This one finally moves out a ways. And by looking at how close those isotropical lines are to one another, you can tell how steep the terrain is. You can plot electric fields and their potentials in the same way. Now in this case, you've got a nice uniform electric field. And it has, at that electric field is so many volts per meter. So you plot a line every so many volts. They're going to be a certain number of meters apart. You'll get nice, uniform, perpendicular lines of equipotential, or equipotential surfaces in a 3-dimensional electric field. What you're going to see tomorrow is, hopefully you've got this nice E field plotted out like so. And you're going to sit down and measure equipotential surfaces or lines in lab. And you're going to plot them out. You're going to find out that, okay, well here, and here, and here, and here, and here, and here, my potentials are all the same. And then you plot them out this way. And you do the same thing here. And the same thing here. And you plot one right down the middle. And you will find out, hopefully tomorrow, you find out in lab that you get these equipotential lines that are everywhere perpendicular to the E field that you've spent a week calculating. That's the gradient of that electric field. That electric field is so many volts per meter. And those, when you measure out those equal lines of equal voltage, then you're going to find that they're all that certain number of meters apart, depending on the strength of the E field where you plot them. But they will be everywhere perpendicular to the lines of the E field. That's a gradient. That's why it's called a gradient on the side of the road. Yeah, I'm out of time, I know. On the side of the road, when the hill slides down, the steeper it is, the steeper the gradient. The stronger the electric field, the steeper the gradient. The more volts you go through in a given distance. I'll see y'all tomorrow for lab.